Okay guys, welcome back. What do you mean by functional dependencies? Sometimes they give you like database design. You come up with a design. That's what happened to you. The phase one, then after that you convert, you came up with a schema. How can you tell whether your schema is good or not? There is a way in order to refine your design, have a good performance at the same time. It's like there is no loss data in general. So generally speaking, in order to decide how whether the design is good or bad, you can say you want to make sure that the design you come up with, you are not going to lose any data. What does that mean here? That means if you store something in the database, for example, I said student ID 1 and the password, for example, XYZ, or the name, this information. When you retrieve the data, we're going to find whatever you store. So data is not going to be changed. Okay? So you put data in, you get the same data out. When you store the design your data, whatever you store something, you'll still be able to restore whatever you submit. Okay? The second thing, we wanted to have a good performance. The main focus here for this class, we just focus in the integrity, which is going to be, we need to make sure I'm not going to lose any data. Okay? The performance, different story, but right now, main folks come up with the design, is not going to lose the data here. Okay? I will start talk about the functional dependencies. Before I talk about the functional dependency, I need to define what's called the normalization. We need to define what do you mean the normalization, then why we need to have the functional dependency. The normalization is the database design technique which allow us in order to reduce or get rid, I cannot get rid of the data redundancy. Let's say reduce the data redundancy and eliminates what is called undesirable characteristics like insertion, deletion, and update anomalies. I'm going to explain this one in the next few slides, okay? So it looks like a mechanism to make sure that my design doesn't contain a lot of redundancy. Or, of course, we try to eliminate the entire redundancy, but we can't. So that's why you reduce the data redundancy. And also, we don't have like undesirable characteristics, like to say whatever insertion, deletion, anomalies. Okay. So in other words, you can have a design which I'm encouraging you because I received many questions about the design. How can you make sure that my design is great, correct 100%? Okay, so you can use this technique. It's going to be a good idea if you try to apply whatever you're going to cover in this chapter in order to refine your design, even for the future. Because right now the goal here, just give you an idea how to design. Then once you start working, you need to show your boss that your design is correct. Yeah. Okay. So anyway, in order to do this normalization, it looks like we have a multi-step technical process, okay, which takes data, but in one table or table. Then after that, starting removing duplicate data from the relation table. So we start with a one relation or set of relations. Then once you find one relation or table that has bad anomalies, is not good design, then in this case, you need to make it good design. So you need to decompose this one into sub-relations, sub-tables. How can you perform this one? I'm going to use a set of terminology or mathematical notation called functional dependencies, which allow me in order to check whether the data is a good design or not. Whether you have a problem with this data, then how can we fix it? Okay? So a functional dependency is generally speaking defined as a constraint between two sets of attributes in the relation. And it plays a vital role in order to find the difference between good and bad database design. So that's why it's very important. Okay, so that's why I need to start with a functional dependency. Then after that, we're going to see how can you use this one in normalization. We refine the database, make sure my design is correct. Okay, so I'm going to cover these topics. First, how can you design, or how can you tell whether the design is good or not? How can you tell your design has a problem? Okay, what kind of features are going to be had in this case? Then I'm going to, after that, talk about the functional dependencies. Okay. As I mentioned, it's going to be with a set of constraints that we have within attributes within, let's say, a single tuple. Okay. Then after that, from this one, we're going to take a look and start computing what is called canonical cover, which is the minimum set of functional dependencies that we need in order to reason about whether, by instance, if the schema is correct or not. Then after that, we're going to talk about how can we use a functional dependency in order to perform schema decomposition. Okay. Maybe it's still not clear, but it's going to be clear in a few minutes. Okay, let's take a look at the first one. In order to answer this question, what is the good design? Maybe it's easy to find out what is the bad design. Okay, you can figure out. Give you this. So we do have here what? ID, name, salary, department name, building, budget. So it looks like we have instructor relation and department relation. We put this one in one table. What do you think? Is this good design or not? You might have this design, okay? You end up will have something like this. So I said, now it's good or not? Take a look here. It looks like we are going to repeat a lot of information. This have many redundant repetition, okay? Or many redundancy in the data. Take a look here. For every single department, we're gonna repeat the building budget. Building budget. For example, take a look at the computer science department. Okay? Computer science department. For every single computer science department. And etc. So we're repeating, data here. Okay? If you compare this one with the situation that we have, the department can be a separate or independent relation. So inside this one, the building and the budget can be repeated for every single department only once, but here repeated many times. It depends how many instructor or how many employee work in this department, right? We don't like this one. Let me go into more details, talk about the insertion, deletion, and update anomalies. Let's take a look here. If you give me this table, you come up with your design, even in the class project or later. You come up with the design, you have a data stored in the table, take a look at each table or relation and see, do you have updated anomalies or not? That means if you want to update or modify, let's say, specific attribute, are you going to modify many tuples in this case or not? If yes, that means you do have updated anomalies. Take a look here. I want to update the budget of the computer science department. Oh, that means the budget. Look, I need to access tuple, I need to access tuple, I need to access tuple, and maybe more. Oh, this is not a good idea. Okay, so there is a problem. You do have updated anomalies. The problem with the efficiency, you need to access the entire relation in order to fix this one. I know right now we have only 5 or 3 tuples, but the real application of data maybe have thousands or millions of records. Okay, it might be have a potential for error because we need to make sure that to change this. Data. You need to scan the entire relation, make sure they need to update the entire budget for the computer science department. If we miss one of them, then we have inconsistency of the data. Okay, the second thing, or the second problem here, you can specify here and see whether you have delete anomalies or not in your data. So take a look in this data here. What do you mean by the delete anomaly? If you delete something, you're gonna lose information. That's the meaning here. So take a look. What if you delete, say, computer science department? Okay, all the computer science department. If you delete this one, and delete this tuple, and delete this one, what's gonna happen here? You are going to delete this employee, and you're going to delete this employee, and you're going to lose this information. I want only delete the department, not the employee that's working in this department. I cannot do this one. I do have a problem. So we are going to maybe lose multiple tuples in this case, right? For example, assume that you're going to delete the department that has only one employee. If you delete this department, you're going to lose information about this employee. Or you're going to assume that you're going to delete, for example, this employee that's stored here, someone is stored here, okay? And he's the only employee in this department, XYZ. So if you delete the employee information, this tuple, you're going to delete all the information about this department. I'm losing this information about this department. You see that we do have a problem here in your data, with the structure. So that means something wrong with this table. So we need to fix it. Again, this is going to help you in your design, in a class project. By the way, you can do this one even after the semester is over, okay? If you wanted to continue working your class project in order to make sure that you understand the material. So I encourage you to go over this slide, try to fix this one, try to see whether you have anomalies or not. I'm talking about the design, I'm going to talk about the application itself, the code that you use in order to access the data, etc. That is, you can do this one in your own time. But the most important thing, you still sometimes, if you are not confident, your design 100% correct, you can apply these techniques. See whether you have some redundancy or not, anomalies in your data or not. If yes, this means something wrong, then you need to fix. And I'm going to show you how to fix it. Okay? The third one of this anomaly is insertion anomalies. For example, assume that you are order to insert instructor that doesn't work in any department yet. So in this case, I need to, for example, if you insert this instructor, I do the ID, the name, and the salary. I don't know the department name, building, and budget yet. So I need either I'm going to use a dummy department dummy data, maybe I'm going to use with fake information, or use a null in this case. Yeah. And the same thing, if you try to insert a new department that there is no employee works in this department yet, so in this case, I need to insert dummy data for the instructor data. So in this case, it looks like putting this information is something wrong. Okay, how can you fix? We're gonna do decompose. This means in this case, if you have this kind of anomalies, if you have a lot of redundancy, so in this case, you're gonna end up this with the conclusion states that you put too much information together. You need to decompose them. Right now, we're going to do this one like by locking. Later, I'm going to show you using the functional dependency, how can you do that? Okay? So in this case, since we have this anomalies here, we need to do what? I need to decompose my data. Okay? When you decompose, that means I need to split this data. Somehow, if you manage to split, this one is going to be in the structure, and this one is going to be in the, let's say, department. So in this case, yes, we don't have a problem. Okay? So does that mean combining relations bad idea? Not all, not in every situation. It does mean if you have a combining two relations, one relation say, oh, that's bad idea, they need to split. No, not all. Okay? Remember we talk about the section, and we do have a section relation, or okay, section class. We use this one as a relationship between the section and the class. And in this case, we did what here? We combined them in one relation, right? And this relation that contains all the information. Here we don't have redundancy in the data. There's no repetition of the data in this case. So in other words, the problem here, we cannot say all the combining data is bad idea, and at the same time we cannot say decomposition is bad idea. So we need to figure out a way, a scientific way in order to decide, yeah, in order to tell. That's why we need to understand, take a look at the functional dependencies. Before we talk about this one, let's give you an example for the decomposition. So assume this information about the employee, okay? And assume that when you say not all the decomposition is good idea because some decomposition is bad, decompose, that means you start one relation, split this one into sub-relations, two or more, okay? Assume we give you employee, have ID, name, street, city, and salary. And you said, okay, I'm gonna split this one into two relations. The first one has the employee ID and name, and the second relation then contains the employee, name, street, city, and salary. It's a clear bad idea. Why? Because if you remember, we don't want to lose data. So I want to make sure that I'm being able to receive the information about the employee. Okay? So the problem that using here, when you try to join this relation, the sub-relation, decompose the relation, you are not going to produce the same relation. So we call this kind of decomposition is lossy decomposition, which is bad idea. Okay, we cannot reconstruct the original relation, so in this case it's going to be lossy decomposition. Let's take a look here. Why is lossy? Take a look. So we have the ID and name here, and we have, you say, name, street, and city. Assume that we do have an instructor, two different instructors. They have two different, ID, but they have the same name. Okay, and this common situation might be the case when you have your data. This situation, how can we handle this case? You decompose this one here, so you have a Kim here, each of them here, Kim based on the name, and this is street. Now, if we try to get that's what I have in the data, okay? In order to perform my query, I need to join these queries, the decomposition. Yeah, decomposition requires from me in order to achieve the data to join them in order to produce the same result. But remember, I split them in order to remove the redundancy. But we can join them in order to get the results that you're looking for. That's fine. The problem here, you're going to produce too much information. Let's say you're going to have more tuples, but we have less information. What does that mean? You're going to lose information. Why? I have more tuples. But right now here, can you tell me, for example, you can't tell, by the way, in this case, there is someone, okay, living in a specific street, a particular street, city, salary, has specific salary, okay, and return to someone named Kim. Which Kim? I cannot tell which one. And the problem here, you see that Kim, this Kim, there is someone, his name is Kim, living in this address, or this information. There is someone Kim living here. There is someone Kim living here, someone living here. Which one here? I cannot tell here. So that's the problem here. If you have lossy decomposition, When you join two relations or decompose two relations, you cannot produce the original one. You're going to lose information, although we have more tools. That's bad. Okay? So this one kind of decomposition that we don't want. Of course, I don't want it to perform, use this one as a human, take a look at the results, say, oh, it does make sense. Oh, does that make sense? We need to find the mathematical notation or scientific way in order to help. Okay? Lossless decomposition, that's what I'm looking for. That means if you have a relation R, and you compose this one into a set of sub-relations, R1 and R2, or maybe more, okay? Maybe more, okay? By the way, as I mentioned at the beginning of this semester, we start looking at the relation R, the instance, etc. We've said that the uppercase, generally speaking, when you use this one, that means I'm talking about the schema. So when you have the schema relation R, or the original relation, you divide this one into R1 and R2. That means I'm going to redistribute the keys or the attributes, among two relations. Okay? So it looks like in this case you project this, you have the relation R is going to be project the list of attributes R1 from R, and for the relation the R2, you're going to project the list of attributes R2 from R. If you join them here, lossless decomposition is going to produce the original relation. So in other words, looks like if you have a take a look, somehow you're going to organize the data here, divide this one into two relations, sub-relations or more, and when you perform a join, these sub-relations are going to produce the original relation. And actually we can do this one using what? What if we define this one as the ID? Oh, if we do this one based on the ID instead of the name here, so yes, those relations are what? Are lossless decomposition. Why? Because if you join them, this relation, you're going to produce the original relation here. Remember, I'm joining based on the ID. The ID is the primary key. There is no duplicate, so the ID can tell me exactly which one is going to be joined with this one. Must be equate based on ID. So in this case, yes, I can do that. Okay? So this is an example. Assume that you have a relation R is going to ABC in this instance, two tuples, for example. You can, this one based on what? I'm going to do, for example, based on the R1 is going to be AB, and the R2 is going to be, let's say, BC, okay? And since B is not repeated, so it looks like B is the key here, okay? And also you can use A, the key, based on the data that we have here. And C2, the meaning here, somehow, when you perform distribute or decompose your data into two sub-relations, we're going to use what? You're going to do this one based on the primary key somehow. Okay? So again, we have AB and BC. And that's what we did. Project based on the R1 with a set of attributes, and project based on the R2 with a set of attributes. Both of them belongs in the relation R. Okay? When you perform natural join between these sub-relations, since P, I will use a common key, and B is the primary key, it looks like. So in this case, I'm being able to construct the original relation. So this good decomposition with lossless decomposition. Okay? So what the function dependency? So the function dependency estimate, you need to find a way in order to help me, your scientific way in order to tell me whether for example, this decomposition is good or not, whether it's a flaw or an issue or redundancy, and etc. So the functional dependency is defined as what? Assume that a functional dependency between two attributes or two sets of attributes, okay? It's defined as what? It's going to be a relationship between, two attributes. That's the way how to write the functional dependency, by the way. And I say F functionally determines Y, or Y determines by F. It's like a relationship between two relations, or two sets of attributes, okay? Implies that the value of X, in this case, is uniquely identified the value of Y. For example, if value of X equals 5, definitely the value of Y equals 6, for example. Okay? The simple thing you can see is the ID with, they say, name GBA. It might be, by the way, set of attributes, either one or two, and not unique, they say, relationship between two attributes. When you say two attributes, might be two sets of attributes, okay? So in this case, you're going to say what? The IDs uniquely identify the name and the GPA, right? Yes, because with a simple ID will equal 1, you can maybe the data can be Alice and Bob. So if the ID equal 2, it's going to uniquely identify another table, another information, okay? Functional dependency is like constraint of the data, form of constraint, set of condition or rule you need to enforce in your data in general. Okay, so the basic idea behind the functional dependency is we have a value of, let's say, variable depends on the value of another variable. So take a look, might be the name of the GPA depends on the ID. Or in this case, y, the value of y depends on x. From where you get this information, this constraint from the design of database that you try to design, okay? For example, the simple thing is the serial ID with the name. So in this case, because the name depends on the serial ID, in this case, the serial ID is going to imply the name. That's the meaning here, okay? So before we talk about more details of functional dependencies, just to remind you with the legal instance. The legal instance is what? If the database is one that where all the relation instance are legal instance. What do you mean the legal instance? This means the instance of every single relation is going to satisfy all the rules, all the constraints that we have. For example, if the rule is said the GPA must be between 0 and 4.00, we will never find any instance, we call this one a legal instance, that contains the GPAs beyond this range. Or we could enforce form key constraint. That means we never find department name in the student relation, for example, where this department is not listed in the department relation. We don't have this one. That's what we call legal instance, okay? So the functional dependency, again, is going to be like formal constraint. And we can use the functional dependency in order to, as a generalization of the notion of the key. I'm going to go over this one later. But right now, let me double check for the functional dependency. We said what? It's like a formal constraint, and it's like a value, to say of a variable or the set of variables depends on the value of another variable or a set of variables. Okay, let's do this one with more details. How can you do that? How can you design, or how can you figure out, how can you check that? The way that we write the functional dependency, we said x implies y, x determines y depending on x. Okay, so the value of y, in order to get the value of y, is based on the value of x. Okay, can be determined based on the value of x. How can you define that? So this is the formal definition of functional dependencies. We have, for example, we've said x functionally determines y, implies y determines by x, okay? Can be defined as following here, okay? So this means for any two tuples, T1 and T2, okay? If these tuples agree on the value of x, what does that mean? That means T1 of x is equal to the value of T2 of x. If they agree on the value of x, that means these tuples must agree on the value of y attribute true. So it means must be agreeing on y. That means T1 of y must equal the T2 of y. That's why in this case we can say, in this case, x implies y, or y's function determines by x. Makes sense, yeah? You remember we said, when you define this one, you said a value, or you say a set of an attribute, as I mentioned here, we said the value of attribute or variable of set of variables, in this case y, is what? Depends on the value of another attribute, within this case is x. So that means in order this one hold, this is the definition, formal definition, say x determines y, means that for any two tuples, if there is any two tuples relation R, for every single two tuples relation R actually, if they agree in the value of x, so to go to the tuple 1, check the value of x for T1, and this one, if they equal the value of x to T2, then in this case, the value of y in the T1 must agree in the value of y in the T2. Otherwise, it doesn't hold. This is the functional dependencies. Okay? This is the definition. Let's have the example here. Assume that we have this order A and B, and this is the value here. Let's take a look. Do you think B functionally determines A or not? Yes or not? Not. Yes or no? Remember two tuples. If T1 of B equal T2 of B, that means must have, should have that T1 of, let's say, A must equal T1 of A. So take a look here. In this case, since we don't have any tuples, so it holds in this case. So you see that 4, we have 1, we have the T is 5, 1, 7, and 3. We didn't have a tuple here. There are two tuples, so it's hold in this case. But if we take a look A to B, no. Why in this case, if we take a look A to B here, why it doesn't hold in this case? Take a look here. A, if you have two tuples that have the same value of A, so this tuple and this tuple, they must have the same value of B in order to say A determines B, or A implies B, or B determined by the value of A. Yeah? You see that here? So this one, no, because we have an issue here. Clear? So this is the functional dependencies. Okay. How can you, what's the relation between this functional dependency and the key here? I'm going to go over the same definition. This is very important if you take a look at the same definition that we have. Assume that we have the relation R, okay, the set of attributes in the relation R. The small r, that means an R, that means this is the instance of the relation R, okay? Anyway, assume that we have a set of K with a set of attributes that's subset of this relation R, okay? A set of, might be all of them, subset of the relation R. I'm gonna say K is the super key in the relation R. F and only F. K uniquely determines R. So what does that mean here? If you have this situation, K uniquely determines the relation R, what does that mean here? That means if we have a two tuples, T1 and T2, in this relation, both of them agree on the values, say, of K of T1. That means they must agree in the values, say, the R. Right? When you say R, that means all the attributes. So if we have this situation, I said K is going to be super key here, this is not only happen if the T1 is equal T2. Right? Otherwise, we did have this equation. Make sense? So that means in order to define K as a super key, you can say have functional dependency, K determines Y. So that means we have a subset of attributes. The value of this subset of attributes is going to uniquely determine the value of what? All the attributes in the relation R. And in this case, you can use, if this one unique, every two tuples uniquely defined, they have the same value based on this attribute, and it can unique an entire relation. So in this case, the only option that happens if the T1 is not equal to T2 in this case, right? So that means there is no tuple they're going to have like the same set of attributes, okay, which uniquely identify the entire relation R. So in this case, we can say, I will define in order that this one can be super key, there must be K super key must be has a function determined the relation R here. Okay? Hopefully that makes sense to you. So we know now what do you mean the function depends. The like relation between value one attribute is going to be defined, for example, or imply or determines the value of another attribute. Okay? We can use this one as what? In order to, as a notion of the key, define this one is going to be a key here. So K, function dependency, hold the relation R in this case. If the K uniquely determines the relation, the entire relation R, uniquely identify any tuple in this relation R, or the value of K is going to be uniquely identify any tuple in the relation R, so it's going to be super key. In order to find the candidate key, we can perform what? You can say K must be super key, and also at the same time, K must be minimal. Minimal, what does that mean? There is no subset, you cannot break it down to the subset of attributes, and one of them at least is gonna produce or can generate to say super key. The same definition that we did before, but only here we can use this one using the the function dependency. So here that means there is no alpha subset of K, which alpha is going to uniquely or it's going to be super key in the relation R. So in this case, I'm going to say K is a super key, and now it's a candidate key. Okay? Let's have this one example here. Take a look at this relation. We have independent, instructor department. We put everything in one relation. The key here we said we have the ID and the department name. Okay? This is the super key of this relation. So generally speaking, if you take a look here, the candidate key is going to be the ID, or we have the department name. Both of them can be uniquely identifying the tuple of this relation, kind of, although both of them must be exist in order to produce what? In order to uniquely identify all the tuple of this relation. Okay? So take a look just for the department name. The department name is going to be uniquely identify the building, right? Right. Yeah, because it's going to be key here. And the department name actually, the department name is going to, determine what? It's going to determine the building and the budget. So if the department in computer science, you're going to have the building, Stuart building, for example, the budget $1 million. If the department in the math, that means you're going to have the building here, specific building, and the budget, I don't know, $100, $1,000, and etc. So the ID in the department is going to be the super key. Why? If you take a look, both of them, the value of ID and the value of department, since they are primary key here, I mean, this is going to be a key in this part of the relation, can uniquely identify this tuple, and this one is going to be uniquely identify this tuple, so it's going to be the primary key of this relation. Okay? Where it's going to be the super key in general. So in this case, the ID and department name, for example, for any single two tuple, T1, okay? Any tuple T1, okay? If they agree on the value of the ID and the department name, they must agree on the value on the material. They have the same value of the name, salary, building, and budget for any two tuple T1 and T2. But in this case, since it's going to be the key, this means this will only happen if the T1 is equal to T2. That means I'm talking about the exact tuple. Okay? Whether it's going to be generator can tell me whether the key or not. Whether it's going to be function dependency is going to be hold or not. The question here, why you should care? Why you need to learn this one? I'm still not convinced. Okay? So the function dependency, for example, is very important here. Okay? Because it's gonna be allow me in order to check or decide whether my database is good design or not, is correct or not. Okay? Of course, we do have a problem with the function dependencies, because I cannot implement this function dependency using this database management system. It doesn't support the assertion with the way that how can you use the function dependencies. Okay, we do have a problem with trying to basically understand it. How can you achieve the performance? How can you validate every single function dependency based on the entire table? Because every time you try to insert, modify the data, you need to check this one against a set of rules. Remember, function dependencies with a set of rules that you need to enforce, a constraint that you need to enforce in your data. Okay, every time you modify and try to change the data, you have to check this one against any existing functional dependencies. If you found any violation, then stop. You cannot perform this operation. Okay? So, since I cannot define them in the original data, so how can you use them? Again, you use them only for the design in order to tell whether your design is correct or not, and how can we fix it. The first thing, you take a lot of different types of functional dependency. We call this one trivial. With the simple thing, that means we call this functional dependency trivial if the right-hand side is subset of the left-hand side. Okay? So this one, if we start using alpha and beta, okay? Alpha is going to be the left-hand side and beta is going to be the right-hand side. Based on the definition of functional dependency here, we have any two tuples, T1 and T2. T1 of alpha, if I agree, equal T2 of alpha. That means in this case, in order this one to be held, that means T1 of the beta must equal to 2 of the beta. Right? So this is my condition that we have. Good. So if we have, for example, you see, the right-hand side is subset of the left-hand side. So this one trivial. So I'm not going to say, for example, ID is ID. Okay. ID, unique ID. That means if you have a two tuples agree with the value of ID, they must agree on what? The value of ID. Come on, wasting my time. It's trivial. There is no need to ask this one. Okay? That's one thing. Good. How can you define this one? Lossless decomposition uses the function dependency. How can we test? In order to test this one, since we have a relation R, you divide this one into, let's say, two sub-relations, R1 and R2. Maybe you have more up to Rn. Whatever, you have more than two sub-relations, it depends, but just for simplicity, assume that to simplify the process, I'm going to say R is going to be divided into R1 and R2. Okay? When you perform that, now we need to check whether it's going to be this decomposition good or not, whether it's going to be lossless decomposition or not. In order to check this one, you take R1, intersect with R2, and talk about the attributes, and see whether either it's going to be identify R1 or R1 is like R2, it's going to be a key in the relation R2. Remember we said K is going to be key of the relation R. This is the definition of function dependency. We define this one. Yeah? We said if two tuples agree with the value of K, it's going to be, this means every single two tuples is going to be agree with the value of R, and two tuples. But in this case, since it's a key, that means it never happen unless the T1 is equal to 2 in this case. Or we're gonna talk about the same tuple. So in this case, you're gonna intersect the here the two relations, the attributes, and see whether it's gonna be key, it's gonna be relation R1 and R2. Why? The key here was that means if we have a key intersection between R1 and R2, there is a common attribute between R1 and 2 is a key. That means when you try to join this relation and being able to reconstruct the original one. Yeah? If you remember the example that I give to you here, when you've said here, assume that here, I define this one, use the ID here, and the ID is going to be the key here. So if you have the ID here, so it's going to be 57766 and 898776. When you join this one here, you're going to produce the same relation, not this one. So you are not going to lose them for me. Why? Because here R1 and R2, it's going to have what? When you intersect them, it's going to produce what? It's going to produce the ID. The ID is what? Is the key in the relation 1. And also, the ID is the key in the relation 2. So either it's going to be what? It's a key in this relation. The key is super key. If the super key, if either of them, or any of these relations, that means this is enough to allow me in order to rejoin the relation. So I'm being able to reconstruct the original relation without any key. Any loss information. So that's the way, how can we test this one whether it's going to be lossless decomposition or not. Okay? This is a very important slide because in one question in the exam, definitely give you like functional relation or original relation. Then it give you like a set of say sub-relations, decompose this relation into sub-relation, and you need to decide whether it's going to be this one is going to be lossless decomposition or not. You perform the intersection and see whether you're going to have a key or not. Someone is going to say, how can you decide which key or not? I'm going to show you that how can you decide the key later. But right now, since the easy thing to say, you can't tell this is the ID, it's going to be the key. Okay? I'm not going to give you example in the exam question, something like the ID, name, etc. I'm going to use ABC because it's easy to work with this one. Okay? So in this case, assume this is the original relation that we have. Since we have anomalies, etc., we said that we're going to reconstruct, we decompose this one into two relations, sub-relations. The first one is structure, the second one is department. When I intersect both relations, I just say R1 and R2. I'm going to check whether it's going to be good intersection or not, good relation or not. So the R1 intersect with ID. When you perform this operation, it's going to be based on what? Based on the department name. And the department name is what? Is the key in the R2. So yes, this is lossless decomposition. Why? When you reconstruct that, perform a join, if you try to find information about the ID, name, salary, department name, building, budget. So in this case, I need to join, join the instructor with the department or R1 or R2, since we have the intersect. We do have like a common attribute between these relations. It could be the primary key or super key in any relation, given relation, sub relation. In this case, it could be the department. So I'm fine. I don't have problem. It's going to be reconstructing the relation. This is a simple example, and again, this is very important, something similar. So if I give you a relation R, I give you the set of functional dependencies that given there. So I give you the value of X with the set of functional dependencies that associated with this relation. So that means this is proof. That means A determines B and B determines C. Okay? Decompose, for example, different ways. For example, I decompose this one like this, based on R1 AB and R2 is BC. In order to check whether it's going to be lossless decomposition or not, take R1, intersect with R2. What R1? A and B, intersect with, say, B and C. And the result is going to be what? B. Okay. B, I note that determines C based on the function dependency. That's the way how can you decide whether your function determines or not. That means the value of C must determine the value of B. That means if two tuples agree on the value of B, they must agree on the value of C. So yeah, looks like here. Yeah. So here in this case, B determines C, or you can say B determines BC. And B is trivial. I'm not going to add this one. So this one here, B, they'll be key in the relation R2. So yes, this is lossless decomposition. That's fine. If you could use a different way, another way to decompose this relation, We have R1 and R2. R1 is AB and R2 the AC. Then you decompose this one. Okay, let's check whether lossless decomposition or not. Intersect them, and that will have A, and A unique that determines the value of P here based on the function dependency. So A determines P, which is going to be a key here in this relational. R1. Okay. I can give you more details about how can we do this one, how can we come up with a key, prove this B, for example, key in the relation, and A is going to be key in this relation. I mean, for the R1 or R2. Okay. Another thing I need to go over here is called the implied function dependencies. Sometimes I give you like function dependencies, and they want from you to check whether this function dependency is violated or not by any instance. You can check this one for the give you function dependency, give you an instance. You can't tell whether the function dependency is like violated or not. Yeah, remember something like this. This one, give me a second. Yeah, here. I give you a function dependency, and I say, check this one whether it hold or not. Based on the instance, yes, you can tell whether this one hold or not. But you cannot prove that function dependency is a part of the schema using an instance. So I need to have more details or the schema in order to decide whether it can be hold for every single schema or not. Because based on this data, yes, it's hold. Yeah. So I'm going to talk about the implied function dependencies, okay? And when you talk about the implied function dependency, maybe I give you a set of function dependencies, like the value of f here. Then I said, I want from you to decide whether specific function dependency is hold or not. You cannot test against every single instance because I'm not going to give you the instance. So you need to find a way, one scientific way, in order to decide whether this set of the given function dependency is hold or not. So the simple thing here, you can do what? You can take a look and compare this one using the set of function dependencies that we have. For example, if I said, check for example, if A determines B is hold or not. Oh, I do have a set of function dependencies. I can tell, yeah, it's hold because it's given here. How about, for example, A to C? If by just comparing here, you're going to say, oh, it doesn't hold. Actually, it's hold, yeah? Because we do have another, when you give you a set of function dependencies, there is another set of function dependencies that can be derived from this given function dependency. I didn't write them here, but you can imply them, you can derive them. For example, if it looks like you take a look, A determines B, which B determines C, so you can say, oh, A is determines C. So you see that? This one, you can imply, or you can imply this one from the given set of function dependencies. So this one, yes, it can be hold. How can you do that? So I need to rely on whatever provide function dependencies. Then now I'm going to show you the way how can we derive a new one, additional set of function dependencies. We call this one the implied function dependencies. Okay? In order to do this one, I'm going to use what is called the closure. Okay? So what the closure here first, I think, yeah. Before I go over this one, I can give you something called the closure. What the closure? Closure given, for example, is going to produce all the possible implied dependency given provided function dependencies. If you give me the set of function dependencies, here, for example, let's go back, something like this, I can use the closure, which is going to provide all the possible implied dependency given the provided function dependencies. When you talk about the closure, that means you can come up with the list of all attributes that can be produced or can be achieved using this set of given function dependencies. I'm going to talk about this one right now. Ignore whatever about the closure. Now, let's take a look. I give you a set of function dependencies here. Then I want from you to do what? In order to compute all the implied set of function dependencies. I'm not going to ask you to in the exam to how to imply this one, but just to give you an idea, how can you do something like this? Okay, we are going to use Armstrong axioms in order to produce a set of function dependencies, or the implied, okay, or compute the F closure in this case. F closure, we define this one, all the possible implied dependency given our provide function dependency. So in this case, we're going to do what? Using this rule, the first one is called reflexivity. So in this case, you have what here? The right hand side, the subset of the left hand side. If the right-hand side, subset of left-hand side, that means we can take a look and produce this functional dependency. For example, if you take a look, you have A, B, C, and you have A, B. This one is subset of this relation, so that means in this case I can produce this functional dependency. Okay? Augmentation. What does that mean here? You have, for example, alpha determines beta. You can just add the same attribute, for example, gamma, left-hand side, gamma to the right-hand side. It's not going to affect anything, so we come up with another functional dependency. Transitivity rule, another thing. Remember it said we have A determines B, and you do have a B determines C. So you can end up, you have said, okay, it looks like A determines C. This is another functional dependency we can perform here. Okay? There is additional rules, which it can be actually, you can use only the Armstrong axiom in order to produce all the implied functional dependencies. Or you can use this one union, which is going to be actually the similar, all of them union, decompositions, like pseudo-transitivity rules, all of them is going to be inferred from the Armstrong axioms. Okay? What do you mean by union? For example, you have A determines B, beta, sorry, example. And you have a beta determines gamma, for example, something like this. Okay? Oh, sorry. And yeah, let's say A determines B. Okay? And you do have A determines C. So in this case, you do what? Since the left-hand side, the same value, you can say the left-hand side and combine whatever you have, union the right-hand side together. That's what's called the union rule. The other rule is called decomposition, with the reverse, the opposite of this operation. So you have A determines B, C, you can end up, you have A determines B and A determines C. Yeah? Pseudo-transitivity, that means, for example, you have A determines B, okay? Then you have, for example, C, B determines D, something like this. Okay, so in this case, you say, so A determines B, I can substitute B with A, let's say C with A, and this one is going to end up CA determines D in this case. Okay, you can use them if you wanted to just to test, just for fun. If you have fun, you want to make sure that you understand the material, you understand what's going on. We can use these actions in order to produce, come up with a set of all functional dependencies. Can be all possible implied dependency given provides function dependency F. Okay, so you have F here. You can add more. Yeah, one of them you can add A determines H. Someone is gonna say, okay, how can you get that? You start from A. Here you have A B. It's not working. It looks like A determines B. Yeah, and you do have B determines H. I can use transitivity. Yeah, so this means A determines H, which is the one that I can produce. So this is another one. So if we close, we're going to have whatever F union, for example, A determines H, union, etc. We can add more here. So all of them, if you want to take a look, if you have a time, you can go over this one, check how can we produce them. To prove with additional, to make sure that you understand this one completely, I'm not going to ask you the example about this one. Just I want you to be aware of this kind of operations. Okay. The most important thing here I want to find and just for me to understand what do you mean by the implied function dependencies. Okay, so here if you try to test all of them are going to be doable except this, based on the data that you have here. I give you the set of given function dependency here, and you try to prove all these whether it's going to make sense or not. Of course, proof or disapprove. So how can you compute the function dependency, or the F closure in this case? The set of all function dependencies can be, let's say, implied from F. So it looks like I'm going to use one algorithm. Well, I'm not going to use this one because I have another way to do that. So in order to compute the F closure, or the implied set of function dependencies can be implied from F, do what? You need to find, just to find a way in order to apply this Armstrong axiom. The first one, you start, put everything in the F closure, F plus. And forget F now. For every single function dependency that's stored in the F, you need to do what here? Apply, for example, or the set of function dependencies that we have here. Apply reflexivity based on all the function dependencies stored in F plus. Do try reflexivity, do augmentation, then after that, add the resulting function dependencies that we have into the F or F plus. Okay? Then for every single pair of functional dependencies, try to see whether you can combine them using transitivity or not. If yes, add them. So you're keeping applying this one as long as the value of f is going to be changed until you stop. That means there is no more change. Okay? This is not the good algorithm because this one can take a long time just to compute the functional dependencies or the f prime or the closure of the set of given functional dependencies. But someone is going to say, okay, you keep it given us. I know the functional dependency is good because it's going to help me to determine whether the decomposition is good or not, whether lossless decomposition or not, whether this design data has anomalies or not. Okay, that makes sense. But now you give me the closure. Why need the closure here? The closure is going to help us in order to find what here. One way to do that is going to help me in order to compute, for example, attributed closure, which is going to help me in order to decide, in order to test whether this given functional dependency is implied or not, is hold or not, without computing the implied functional dependency for the whole attribute that we have, or the set of functional dependency for the given set of functional dependencies. The second thing, you can use this one in order to tell whether it's going to be or to say the given of the, let's say, attribute. It's going to be like super key or not. How can you do this one? We're going to use the closure. So I'm going to define the attribute closure, which is by given of the set of attributes, you can define a closure to this attribute of or under a value of f. It's denoted by alpha a. For example, I give you, for example, x determine a. Okay, in order to compute x closure with attribute closure, that means in this case you need to find out a way that how could you find or defined as a set of attributes that are functionally determined by, let's say, x under their set of functional dependencies. Again, so find all the attributes that can be inferred from x on the given schema. So in other words, I will in the fx closure, that means I will start from x and try to find out what the list of attributes can infer, can I reach from x, starting from x. Based on what? Based on the given function dependencies. Once you compute the attribute closure, I can use in order to decide, in order to check whether a given, let's say, function dependency is hold or not. So I've said x determines a. You check the set of function dependency given function dependency f. You don't find x determines a. If you find yes, you can tell. If not, that means you need to do what? In order to find out or check this one, the best solution, you need to compute f closure here. Oh, that's time consuming. Take forever. There is another thing. You can compute the attribute closure, which is again x prime. Okay? Once you compute the attribute closure, you're going to check whether the attribute A is going to be part of the, can be reachable as one of the attributes that produced by the x closure or not. If yes, that means you start from x somehow and you can reach A. Maybe it's not in direct way, but there's somehow direct attribute you can follow in order to reach this one. Okay? So another useful usage for the closure was if someone keeping saying, why should they care? Why you keep adding stuff that maybe I'm not going to use? Actually, I'm going to use here. Because here, you can use the closure in order to what here? In order to check, for example, all the constraints for every insertion, deletion, or update, etc. Remember, if you have a set of rules, or say, set of functional dependencies, f, once someone tries to modify the data, we need to check this modification against every single functional dependency, which is going to be time consuming, okay? It's going to be expensive, okay? So what we need to do, if I'm going to able to produce a minimal set of functional dependencies, for example, it might be, instead you have f equal, for example, 100 functional dependencies, maybe I end up with have a canonical, let's say, simple version, maybe it contains 5 functional dependencies. So instead you perform insertion, deletion, modification, you need to test this one against 100 functional dependencies, against 100 rules, for example. If you manage to check them against only 5, which is going to have the same effect, so in this case, it's going to be perfect. Yeah, it's going to save you time. So, another thing, as you mentioned, you can use this closure of attributes set in order to decide whether a given attribute or set of attributes is a super key or not in this relation, which is very important. So if you give you a relation R, You need to test whether alpha is going to be a subset of, whether it's going to be a set of attributes belongs to the relation R, okay, given. So you need to check whether alpha is going to be like produce super key or not. So compute alpha prime, or the closure. So I'm keeping same prime as alpha plus, okay? The closure of attribute set alpha. Then let's see whether we are going to end up, we have a list of all the attributes that belongs to the relation R or not. If you found all the list of attributes, that means alpha in this case determines the relation R, with alpha going to be key, which is going to be the super key. In order to perform this one, I'm not going to go the long way. I'm going to show you the short way, okay? Which I want from you to, this is another important, because I want from you to compute the attribute set. It's easy if you perform that, okay? So in order to compute the closure of alpha, and alpha might be any set of attributes that belongs to the relation R. It may be 1, 2, combined attributes, etc. Okay? To check whether it's going to be a key in the relation R or not, I need to compute alpha closure. How could you start or compute alpha closure? You start from alpha and check the function dependency, or the set of function dependency given F. You see whether alpha on the left hand side, see whether it can reach any attribute or not. You start on the left hand side, put this one in the result as temporary data, or the variable. For every single function dependency that we have, beta that determines y, or gamma, if beta is going to be a subset of the result, assume that the result, this makes sense, the result equal alpha, then for every single function dependency, beta determines gamma. If beta subset of the result, that I reach beta somehow here, of course start with alpha, then keeping adding data, then in this case do what? That means this one I will take the beta, I can reach gamma here. Yeah? So what I'm going to do, I'm going to add gamma to the result. And keep doing this one, keeping this one. So that means you start with the left hand side, with this attribute, and try to reach whatever you have on the right hand side. And keep doing this one until that you end up that there is no change in the result. Then you have to stop. Then you check whether you start from alpha here, you manage to achieve all the attributes that belongs to the relation R or not. If yes, that means somehow you start from alpha and you end up, we have reached or determined every single attribute in the relation R. So this is the super key of this relation, right? Let's see how can you perform that. I will start with a simple example here. Give you a relation R, give you the set of functional dependencies, F, for this relation, and assume that, let's say, you want to compute that attribute set. I guess in my opinion, A is super key. I want to check whether A is a super key or not. How can you do this one? I need to compute A closure. How to compute A closure? Say a result. This is the algorithm. I wrote this one algorithm here. Okay? So A is going to be alpha in my case. It's going to be A. For every single functional dependency that we have, you find A, or they say beta is going to be part subset of result, yeah? So you see that we have A to B and have A to C. So that means the left-hand side belongs to the result. So in this case, what I need to do here, I can add the result. It's going to be equal A, B, C. The order doesn't matter here. What does that mean? You start from A, you manage to reach B, and you start with A, you manage to reach C. Good? Once you can reach A, B, and C, that means you can check. You can start from B here in order to see what other functional dependency we can infer, we can determine, we can follow. So you do have in the other side, we do have what? B, with the part on the left hand, another functional dependency. B belongs to this part, subset of the result, and we can manage to get here, let's see, A, B, C, H, because B determines H, and here you can say A determines B, and because A determines C. Okay, so you have A, B, C, H. Can you proceed? No more. Done. Do you see? I can't use this one. I can't follow this one because the left-hand side is not part of this subset here. I must have a CG in order to apply this or this. So in this case, we end up. So it looks like the A closure doesn't have the old attributes of R. That means A is not super key. Okay? So let's check whether A is somehow, maybe I need to add something. I will start with A, start A, B, C, H. I cannot reach G. So in this case, maybe good idea, combine A with G. So both of them is going to be like attribute. It could be the closure. See whether primary super key or not. So you start with AG in the result. You say AG. Then you can say A, B, C, G. The order doesn't matter because A to B and A to C, right? And you're gonna A, B, C, G, H because we do have a B determines H, right? Because the left-hand side is subset of the result, that we just add the right-hand side to the result. And since you still have updating data, you can perform this one again and again. What else? Oh, we have CG. Yeah, this one is part of the result, subset here, right? So that means use CG, you can use H. I have H already there, there's no need to duplicate this one. And CG determines I, so A, B, C, G, H, I. Oh, because here CG determines I. Then here what? What do you notice here? You start from the AG, and this one contains all the attributes. That's what the relation are A, B, C, G, H. So AG is a key in the relation R. So there's going to be super key. Make sense? Okay. This is another example. If you use attribute names, it's going to be the exact thing here. Okay. If you try to apply that. Good. So to generalize the process, the usage of the attribute closure, I can use in order to test for the primary super key or not. How? Compute the closure and see the closure will contain for the attributes that you think is going to be the super key or the one in the question. If they're going to have, let's say, produce the entire set of attributes that belongs to relation R, then in this case, you're going to say, yes, it's going to be super key. Otherwise, you stop. Okay? Test whether function dependency is going to be hold or not. The simple perform that function dependency is the hold or not, you do it. For example, give you alpha determines beta. Check whether it's going to be hold or not. Either check whether if you find, for example, alpha determines beta, then done. If not, the problem is not listed in the given set of function dependencies. So in this case, how can I check this one? I can perform this one using what? I need to compute if a closure. It's expensive. I can do alpha closure and see if the alpha closure contains the attribute at the right-hand side or not. So in other words, you start with alpha, somehow using the set of function dependency here, you manage to reach beta. You do something and you have a beta, so yes, in this case, alpha determines beta's hold. If I didn't find beta, that means you start with alpha, you will never reach, the right-hand side, so in this case, it's not, doesn't hold. Which makes sense, yeah? And it can help me in order to compute the closure of F, which is not covered in this class. Kit. How could you find the candidate key? We talk about the super key, right? The super key can do this one, compute the alpha closure, and for example, let's check whether the alpha closure contains all the attributes relation R, so it's going to be super key. We define this one something like this, right? How can check whether alpha is going to be candidate key? Oh, I need to make sure it's minimum. Must be super key and minimum. So in this case, assume alpha contains, for example, A, B, C. Or let's say A, B. This is the super key. I check this one, I compute A closure, A, B closure, and this one produce all the attributes belongs to the relation R, or listed in the relation R. So this is super key. Assume the super key. I need to check whether A is the candidate key or not. The candidate key, you need to make sure it's minimum. What does that mean, minimum? Check. You need to compute A closure, B closure, and see whether any of them is going to produce the relation R or not. If any of them produce the relation R, this man is not super key. Since this one contains only one attribute, you're going to say, yes, it's candidate key. How about, for example, you have the relation alpha, or the attribute alpha can contain, or left-hand side contains 3 attributes, for example. We prove this one is going to be candidate key, super key, for example. Okay? So in this case, in order to check whether it's going to be candidate key or not, you need to find any subset of this alpha. If any of them produce super key, that means it's not candidate key. So here start with A closure, B closure, C closure, then AB closure, then AC closure, then BC closure. If any of them manage to have produce all the attributes R, then in this case it's going to say, no, it's not candidate key. Clear? And that's what we did here. So he said to compute the super key for all the set of alpha, for example, compute alpha closure. So all the entire set. If we're going to contain all the attributes, then that belongs to the relation R, then it's going to be super key. Minimum set of attributes for the attribute closure set of all the attributes of a relation called candidate key of the relation. Must be super key and must be minimum. And here, give you an example here to check, for example, AG. We did this one before. We compute the, let's say, the closure, and to figure out this one is going to be super key because we produce all the attributes of the relation R. Is it a candidate key? It's a check. We check A closure before, yeah? Let's do this one. A closure, check A closure. C, we start with A. We have A, B, C, because A, B, C. Then after that, we have H, because B is H. Then done. So it's not does reach R, so it's not this one, not super key. So that's good sign. How about G plus? So this doesn't produce, a key. So still so far, AG is the super key and candidate key. Check G. G because belong one subset of attribute AG. So G in this case is gonna have what? Only itself. Because they don't have itself and nothing else. Yeah, because they put this one in the result, then done. That belongs to the result R. So in this case, AG, yes, is super key and candidate. And this, how can you prove? You see, using functional dependency, you can't tell. You can, based on the computation, you can't tell whether it makes sense or not. Of course, given by the set of functional dependencies that you have here. Okay? Now we're going to talk about the canonical cover. What do you mean by this case? Assume that they give you a set of functional dependency with a set of rules constrained in your data. Okay? Then, whenever a user tries to perform any operation, insertion, deletion, modification of data, we need to test this action from the student or from the user against each, let's say, functional dependency or set of rules or given rules, and make sure that whether there is a violation or not. If there is a violation, I'm going to stop the action that the user tried to do. Okay? This is kind of like expensive operation. Why? Because assume that we have 100. I'm just exaggerate, okay? Assume that we have 100 functional dependencies, set of rules in F. So every time you get perform any modification or insertion, you have to test all these 100. This is an expensive operation, okay? We can reduce the effort that we need to in order to spend in order to check all the violation by testing only a simplified set of functional dependencies, okay? If we manage to this one, they have the same closure as the given set. The same closure, that means you are not going to lose any information. It looks like you instead you have 100, you can come up with 5 or 10 or 15, which have the same closure as the 100. But since 100 maybe is going to contain some redundancy in the data and the attributes on the functional dependency, you can make it much small. Okay? Smaller or the subset or simplified version. So that's what we call the canonical cover. Canonical cover is what? It's like defined as what? A set of functional dependencies. Okay? From F, or simplified set of functional dependencies of the relation S. So it looks like if you take a look at F, or the given set of functional dependencies, definitely might have, let's say, some extra attributes, some redundancy, some extraneous attributes. So I can reduce this one. Let's give you a simple example. Assume that we have A determines B, B determines C, and D determines C. Okay? If you take a look at this case, you say, okay, this is a set of functional dependency given F. I can come up with the simplified version. What do you mean by simplified version here? I can say, for example, here, okay, I know A determines B, B determines C, so I know A determines C, it can be implied. So in this case, I can remove this one. I can come up with canonical cover, simplified version that contains A determines B and B determines C. I didn't lose any information here because I'm still being able to tell whether A determines C or not, yes, but of course not in direct way. If it's compute the F closure, C closure, this one's going to be equal to the F closure here in this case. You see what's happening here? So I know we have derived attribute, say functional dependency implied, etc. can be derived from original one. I don't need them right now. I need to make it simplified version. Small number of functional dependencies which will allow me in order to have an efficient way in order to, let's say, check or validate every action whether the user try to do the data. Okay? The other thing here, it might be not the functional dependency that we have. It might be have a redundancy. So the functional dependencies must exist, the given one. But we have some redundancy in the attribute. And what do you mean by attribute? Sometimes you have one attribute redundancy on the left-hand side. and maybe have some redundancy on the right-hand side. Take a look at the one, this function depends, A to B determines C. You see, if you take a look here, of course, I'm going to show you how to do that, but by just looking at the data, you see A determines D, D determines C, so you can tell in this case what? A determines C, right? Good. Keep this one relative. Here, we said AB determines C, so it looks like with the help of B or without B, I'm still being able to say A determines C, right? So in this case, it looks like this attribute B is extraneous, is an extra attribute. I can remove it without a change of the set of functional dependencies that we have. Still being able to say A determines C. Since A determines C directly, that means there is no need to hit B in order to help me to determine C here. Okay, in other words, two tuples T1 and T2, given any two tuples, T1 agree on the value A. I don't need to say T1 agree on the value B. That's me T2 and then agree to say A, T2, the P. That means there must be agree T1 must be agree, for example, to attribute C, and T2 must agree in the attribute C. Something like this, yeah? So there's no T because B is not affected because they need to have functional dependencies that can be telling me that. Another thing, maybe there is one extra attribute might be in the right-hand side. So you take a look, AB determines C, D and A determines C here. Okay? If you take a look here this way, you can see that, okay, AB determines C, D and A determines C. So if I remove here, let's say, what if I have this situation? I guess C is like an extra attribute. Can I do this one? Yes. If you remove C here, you're still being able to tell, for example, AB determines C here. Yeah? Because you see, AB determines D, and A determines C, since AB closure that contains A, B, C. I managed to reach C here, so yes, I'm still being able to determine C. So that means maybe reaching C, in this case, when we talk about the right-hand side, it's not required or not depending on the value of AB together. So you can start with AB, remove C from here, and being able to reach C somehow using another function dependencies. Okay, so this value of C in this case, it's not, I mean, it's extraneous. Remember, try to reduce, make it short-term, and etc. In order to perform that, you need to find a way in order, how can you tell whether an attribute, for example, the left-hand side or an attribute on the right-hand side is like extraneous, is extra, is redundant. Okay, right now I'm just using my looking at the function dependencies that you have, we can decide, but you need to have like scientific way in order to perform this operation. Okay, so this is the way how can we handle this. I know if you take a look, you see, oh, it's complicated. It's not complicated. It's like a formula you need just to apply. Okay, so of course, extraneous redundant attribute, if you remove it, is not gonna change, I mean, the constraint implied by F. You're still being able to imply this one somehow. You see that? Yeah, keep in your mind. Doesn't mean you remove then you got to produce different function dependencies. Or you cannot imply this one using the set of given function dependencies. The first formula here, take a look. I have alpha determines beta. That's the given of the set of given a function dependencies. I need to check whether they have, for example, extra redundant attribute the left-hand side or the right-hand side, in the alpha or in beta. Alpha might have a set of attributes and beta too, okay? So attribute delta is going to be extraneous, for example, an extra attribute in the way that F and only F, for example, delta subset belongs to the attribute, so from the left-hand side, and I'm still being able logically imply this attribute using, if you remove alpha, determines beta, and substitute this one with the new value, remove delta from alpha, so add delta to minus alpha, determines beta to the set function dependency F, I'm still being able to reach this one. I'm still able to make alpha minus delta determines beta here. That's the meaning here. Not going to be clear next slide. Just keep in your mind, this is the formula to try and move delta from the left-hand side and see whether it can still, you start with the left-hand side minus this x attribute, you're still being able to reach the right-hand side. In other words, the value of delta is not important. With or without the value of delta, I'm still being able to reach beta. from alpha minus delta. Okay, if we remove this one from the left-hand side. In the right-hand side, what does that mean here? We're going to remove something from the right-hand side. In this case, it's going to be from beta. And what we're going to do here, you're still being able to do what? You're still being able to, let's say, reach beta in this case. Yeah? You start with alpha, and you have the beta. Since the extraneous attribute belongs to the right-hand side, so it's going to be alpha determines beta minus delta. Assume the delta is the x attribute. I remove this one. I change the value of f into f prime, which contains what? The value of f, the original set of function dependency. You remove alpha determines beta, and substitute this one using alpha determines beta minus delta. Okay? So in this case, you start from alpha, closure. You're going to see how to compute this one. You start from alpha, and somehow you're still being able to reach delta in the right hand. So in other words, there's another way, another set of function dependency. We can use them in order to reach the delta. So reaching delta in this case using alpha, it's not important in this case. It's extra because I have another way in order to reach this one. Okay? This is the important slide here, very important. If you try to compute the extraneous and any attributes, so you have to use this one. Okay? So let me try to test whether given delta alpha determines beta, whether you're gonna make for example, I can remove one attribute from the left hand side, or I can remove one attribute from the right hand side. Okay? So here, how can I test? How can I perform that? So let's have 3 stars for this one. Okay? So in order to test this one, you're gonna do what? You're gonna assume, for example, as I think one attribute in the left-hand side is extra, is extraneous, is redundant. You do this one, you say gamma is equal alpha minus delta. Remove this one from alpha. For example, alpha A, B, C, and assume C is redundant, so alpha minus C is gonna AB. This is going to be gamma. Just I put this one gamma in order to simplify the process. It's better to use alpha minus delta. Then after that, I need to check if gamma determines beta or not. That means if I remove delta from the left-hand side, I'm still being able to reach the right-hand side. Identify, implies the right-hand side. Okay, using the so how can you do that? Remember, we said in order to test whether set given function dependencies like hold or not, you need to do what? Compute the closure and see whether the closure contains this attribute beta or not. If beta is going to be there, then we are fine. Okay, so you see, compute the closure based on what in the set function dependency f. So check with f, the original f, and start with the gamma. Could be the gamma closure, see whether beta is going to be bottom. If I found this one, that means without help of delta. Delta is extra, it's a redundant attribute. Remove it, and don't worry, we're still being able to prove or imply gamma, in this case with alpha minus delta. After remove alpha, extra attribute is going to be reached to the right hand side. Okay? To test whether the attribute for the right hand side is extraneous. So in this case, let's do this one. I remove, we have alpha determines beta. And I guess, for example, one attribute here is like, oh, it's redundant. So how can you test that? So in this case, you do the following here. First, you need to compute f prime. What's f prime? You need, in this case, you remove something on the right-hand side, you need to update the set of function dependency. You are not going to use the original one. You're going to use the modified one, the simplified version. So we're going to have, in this case, f minus alpha determines beta. And add, when you say union intersect, that's mean you remove this one, so remove this function dependency, and another one, alpha determines beta minus delta. So you remove the one of the x attribute from the right hand side. And here in this case, I need to compute what? Alpha prime. What does it mean in this case? I want to start from alpha using the f prime, the new one after remove, update the alpha determines beta, and see whether I start from alpha, I'm still being able to reach delta or not somehow. If I found delta here, in this set of attributes, that means this function dependency is not important. It's not, I mean, it's redundant. It's important, I mean, but I don't need to have delta here because it's going to be extraneous or redundant attribute. Why? Because I start from alpha and manage to reach delta somehow using the other attributes. or the other functional dependency. So in this case, delta is extraneous. Let's apply this. Okay, assume I give you something like this. This is the set of functional dependencies. Okay, and you see, okay, something we try to reduce something from here. Someone is gonna say, okay, actually, if you take a look here, you see that A, B is, you cannot remove D because D is important. There's no way to reach D unless you have something else. Yeah, because D is not here, so D is very important. So one thing we can think, this is just one thing help you to decide which one. In the exam, if I ask you to do that, and I want for me to show me how you did that. Even if you choose one attribute and you end up this attribute is not extraneous, it's fine because you show me that you can apply the algorithm. Okay, let's see. So assume that we have AB determines CD. I guess you say D is redundant. Okay, this is from the right hand side. That means you have to go to the next part. So in this case, you're gonna do what in there? I'm gonna start with compute the f prime. Since you modify this one from the right hand side, you assume that something is extraneous, you need to update the set of given function dependencies. Do what f? It's gonna be A, B determines D, A to E, and E to C. Okay, which is the one that we have here. What I've did here, I remove CD, AB determines CD, substitute with AB determines D. Then I need to compute the AB closure, and you see under F prime here, the new one, and see whether you can find C or not. Somehow can reach C or not. So AB is gonna start what? The result is gonna be AB, D, okay, and we have A to E, and E is gonna be give me C. Oh, I found C. Great. So that means C is redundant here, so I reduce. You see, start from here, I end up we have something like this. Make sense? So that's one thing you can perform. The other thing, another example, let's try to delete something from the left-hand side. So I give you like FA determines C and AB to C, okay? And I guess in this case, it looks like you have A determines C. Then I've said AB determines C. Definitely B is redundant. I don't need it. Why? Because I either withheld B or not, I'm still being able to start from A and determine C, right? Because if you move B here, A determines C here. Let me do this one using the formula, okay? Try to test this one. So in this way, I delete something from the left-hand side. Although you can just delete this one and say, oh, there's A determines C, then done. And B is extraneous. So I said what in this case? I'm gonna start looking at the, remember we said gamma, it will be alpha minus the delta. So in this case, gamma is gonna equal to what? It's gonna equal A, B minus B equal A, right? Then after that, I need to compute gamma closure on of F. If you modify and remove something with the left-hand side, there is no need in order to update the F closure. Yeah, I mean the F prime. Just work with the original value here, with the original value of F. If you modify or delete something with the right-hand side, that means you have to modify F prime, original set of functional dependency, modify this one, then apply the closure based on this. Here, gamma prime, okay, closure of F, sorry, based on what? The original one. Gamma is going to be what? So that means A closure. A closure is going to be A, C, okay, done. What you find? You start from A and being able to reach beta, and beta is going to be subset part of the result, then done. So in this case, I can say F equal to what? A to C, and it's going to be A to C. Remove the redundant. Here we have what? We remove duplicate. No, we have the same there, so it's going to be A to C. You see? Instead, you have 2 function dependencies. We end up, we have only 1 function dependency, and easy to do that. This is how can you compute the extraneous? How can you tell whether attribute is extraneous or not? Make sense? If we understand the function dependencies. Okay? Which is like a set define the constraint. We can imply, we can tell determine, for example, a set of attribute value for a set of attributes can uniquely determines. Okay? Implies a set of values of the values of a set of other attributes. Okay. Then after that, we saw that we can use the closure, where we're gonna compute the set of all attributes can be reached from, can be applied from, let's say, given attributes, which is going to help you in order to define or specify what's the primary key, what's going to be, sorry, what's the super key, what's going to be primary key, and etc. And whether the given function dependencies can hold or not. Now we talk about we can use the closure somehow to help me in order to decide whether an attribute is going to be extraneous or not. It's going to be redundant, either the right hand side or the left hand side. If it's the right hand side or the left hand side, that means you do what? You need to compute gamma, which is going to be the left hand side minus the attribute that you think it's redundant. Then compute the gamma prime, or the closure, actually, based on the attribute f, or the set of given function dependency f. If you find out the delta is going to be part of the right hand side, that means in this case, the right hand side with beta is going to be part of the result. You can somehow reach beta. You're still being able. That means this attribute is redundant. I don't need it. So we need just to update the set of our function dependencies in the attribute f and f. If you remove something in the right hand side, so in this case you need to modify the set of function dependency f, which is going to be f prime, which is going to take alpha minus determines beta, and remove this one and add alpha determines beta minus delta that you think this attribute that is extraneous. Then you start compute alpha closure based on the f prime, yeah, the one that I updated with remove alpha determines beta with alpha determines beta minus delta. Then after that you check whether the alpha contains the attribute the delta that you remove or not. So that means if yes, that means there is another function dependency. We can use them in order to find out in order to reach the value of C or not. The same thing that we did here with the second case and here what we did in the first case. Okay, now we know the extraneous. So how can you use this one in order to compute the canonical cover with the simplified set of function dependencies? Instead we use, for example, f. I'm going to use fc with the canonical cover with the simplified set of function dependencies, which can be used in order to have an efficiently in order to decide whether the this action can be performed by the user is accepted or not. It can be proceed or not. Okay. So f logically implies all the dependencies in fc, and fc implies all the dependencies in f. That's basically if a closure closure is equal fc closures. Okay, that's the meaning here. The second thing here, this and interesting. The most important thing is the two property. No function dependency in fc contains an extraneous attribute. That means there is no, let's say, redundant attribute in FC. FC, that means the symbol that we use in order to compute the canonical cover. Okay, that we start computing. The second thing, each left side of the function dependency in the FC is unique. So what does that mean? If you have FC something like this, for example, we have A, B determines whatever, then somehow we have A, B determines something else, I don't care. Then A, B determines something. So this one is not, the left hand side is not unique, it's repeated many times. So in this case, you must have only one time. So you have must A, B determines, and you have to combine whatever you have these attributes in one place. That's what is called unique. Okay? For example, assume that you have something like this, because the student is going to be confused, I mean, based on the previous exams. If you have f equal, for example, a determines b x, y, something like this, and a, b determines, let's say, c, d, and let's say a determines, for example, x, y, z, or something like this. So you take a look. The left-hand side is a, and this is the left-hand side a. This is not. This is different. This contains another. So this one is not. So it's fine. This one is completely different than this one. You cannot say, oh, because here AB, that means this one must be unique. No. This one, the left-hand side, this A, and this left-hand side, they are not unique. Because the left-hand side, they are exact match. Okay? So in this case, in FC, you have to do the following. You have to say A, will be X, Y, Z, you combine this, and the AB is going to be the same as it. Okay, please don't combine this with this because these are different. This is true attributes and this one attribute. Okay, so that means unique. How can you do this one? This is the formula. This is, I mean, the procedure. I know we have a lot of procedure, but the one that algorithm use in order to compute the closure is easy to do that. And the second one, how to compute the canonical cover. And of course, we have like one interesting slide, a very important slide, going to help us in order how can we decide or test whether an attribute delta is extraneous or not, is redundant or not. Either it's going to be the left-hand side or the right-hand side. Okay, this is the formula that we need to follow. First, take whatever you have in order to compute the canonical cover. Take whatever the value of f, the set of function, given function dependencies, store this one in fc, and say goodbye to the f, I don't need you anymore. Then you have to repeat this one in many steps. Okay? As long as the set of function dependencies, I would say canonical cover f, is changed, has been changed, modified, then you have to continue doing this operation. First, make sure the left-hand side must be unique. How do this one? Using the union. So here you see alpha 1 determines beta 1, alpha 1 determines beta 2, so the left-hand side is the same, it must be unique. So you combine the union. How to do this one? Left-hand side repeats only one time, and the right-hand side will be performed union. Whatever you have that with beta 1, union with beta 2. Okay? Of course, you have the beta 1, for example, AB, and beta 2, ABC. Don't say AB, ABC. There's no AB, okay? It's going to be ABC in this case. Then, now take a look. Check. Take one function dependency at a time. Check, we say, okay, whether alpha determines beta have redundant attribute or not. Either it's going to be the left-hand side or the right-hand side. If you found something, that means you need to do what? You need to update the function dependency FC based on the value that we have. I'm using FC. There is no more F done. F is the only thing. Put this one, whatever you have in FC, with the variable you're going to use in order to hold the canonical cover. Then after that, thank you for that. You continue to do this one. If you found, that means you remove this one, delta alpha determines beta and beta, and update this one accordingly. Okay? What does that mean? For example, if I prove delta belongs to, say, alpha is extraneous. That means I'm going to remove delta alpha determines beta in FC and substitute this one alpha determines delta to be. If the right-hand side, do the same thing. Okay? Keep it updated. So let's take a look. How can you compute the canonical cover in this case? The simple attribute, or the simple operation you can perform here, you can use the formula, by the way, that we have. Okay? So the simple thing here, or first thing you need to come up with, okay, you need to compute what? But FC is equal F. So in this case, FC is equal A determines BC, B determines C, and etc. This is the first iteration. Okay? Then after that, check. Make the left-hand side unique. So in this case, A determines BC, A determines B, I need to join them. Okay? In one of them. So union the right-hand side. And this is what we did here. Okay? Sorry, this was the iteration. It was what we did here. The first iteration here. Okay? So this is my first one. I combine them, and we're fine. So the first one, you see A determines BC, B determines C, and AB determines C. Good. Now try to check whether any one of them is going to be extraneous attribute or not. The order doesn't matter. For example, here we check, we try to test whether A in AB determines C, for example, is extraneous or not. Or you can start here with a B or C. With C, actually, you can determine whether C is going to be extraneous or not. Yeah, either is fine. The order doesn't matter. At the end, regardless of the way that you start, you must end up with have the same canonical cover. Okay? So the simple thing here, actually, you can take a look here, see here. Okay. It looks like in this case, let's say this one, I will try to follow the same thing. I do have AB determines C here. So of course, you're not going to say C is not important. It's important. You cannot delete because it has only one attribute. Take a look at the left-hand side. What do you think? Whether A or B is going to be extraneous here? Okay? So one thing you can think about, what if I think A is going to be extraneous? Let's check this one. A is extraneous. That means left-hand side. What you need to perform in this case, in order to check this one, remember if you check the formula that we have in the slide 47, that have what? The left-hand side, that means you have a compute gamma is equal A or alpha minus delta. So it's going to be here, alpha is going to be A, B minus A. So it's going to be B. And you need to compute P closure and F. Yeah, which F? I'm going to use FC, of course, here. This one. Okay, so what's the P closure here? B closure is going to be P. Okay, B is going to be C. Okay, I start with the B and end up with the C. What do you have C? I found which is going to be beta is a part of the result. So in this case, the value of P is not important because A is not important because I start from B, I still being able to manage to tell B determines C. So the value of A is not important, is extraneous. So yes, I prove it. Then in this case, I can end up with have this set function dependency given like this. Okay, what happened here? Actually, we do have a BC and this one gonna be BC because I remove the value of A here. Duplicate because I perform union. That means we have B on only one C, and we are not allowed to have duplicate for function dependency because you're gonna combine them in one, right? So we end up we have to see. We start with 1, 2, 3, 4 function dependency. We end up we have now 2 function dependencies, and we can make it better. Check this one here. As I believe we do have like a redundancy here. Okay, and the simple thing redundancy, I guess it would clear that if you said, for example, B here. Can you remove B? Yes. A determines C? No. Okay, so if you said, can it determine remove C? Yes, because A determines B and B determines C, I'm still start with A and manage to get C. So yes, it's gonna be C, but I can't prove it. So either I can prove using the formula, you can say using the axiom Armstrong axioms, or you follow the formula or the equation that I'll give it for the slide 47 here. So take a look at the second one, the second iteration. For every single iteration, you have to do the same thing. Apply union. If there is a change or not, make sure the left-hand side always going to be unique. Then after that, try to find the extremes. The next iteration, if there is a change, do the same thing. Apply union. If there is a way to do that. If not, regardless, in either case, you have to check whether there is an extraneous or an extra attribute or not. To check whether they have an extra attribute on the right-hand side. As we mentioned here, we're going to believe that C is like extraneous. If C extraneous, remember, if we remove this one from the right-hand side, what we're going to perform here? You're going to use, for example, so delta in this case belongs to the beta, yeah? And delta is going to be equal to C here. All right, that's what we said here. So here we have alpha determines beta. I'm going to take F, C, minus alpha determines beta plus alpha determines beta minus C. I remove C from there, okay? So in this case, I need to do the FC is equal to the following. There'll be A determines B and B determines C. In order to check whether it's gonna be the right thing or set, actually it's clear, A determines B, B determines C, so A is gonna determine C, so in this case, I don't need to have the value of C here, it's gonna be AC, because I'm still being able to reach the C. Right? But let's do the same formula just to make the practice the formula. So I need to compute the A closure based on, let's say, FC prime here. That's I'm going to use FC prime. You need to remember to modify something. I would suspect that we have an attribute on the right-hand side is an extraneous attribute. That means we need to update the canonical cover that we have of prime. What A prime here? So A prime is going to be A, B, C. Oh, I found C with the one that I removed. That means it's redundant here, but I am being able to reach this one, so that means this my function depends A determines B and B determines C, and this is done. We don't have any redundancy. In the example, we give you some question example. At least prove to me at least we have 2 extraneous attributes if you found. Okay, and you can stop that, waste your time. If you give me more, I will give you extra credit. If you manage to give me the final correct for canonical cover, that means that's been good idea. Okay, then again, since we have modification, check whether they have a union rule, start, find the extraneous exchange, now change this the canonical cover. You start from here, and we end up, we have this. Okay, hopefully that makes sense. So we talk about the schema decomposition, right? We said this is a good idea because it's going to help us in order to get the redundant data. Okay, we do have some problem with the decomposition in general, okay? But the first one, when you perform a query, some query required for me to perform is going to be more expensive. Why? Because you are going to split the data among 2 or more sub-relations or relations. in order to combine them to get the result that I'm looking for, depends on the query. Maybe that requires from you in order to do what? In order to join multiple relations, which is going to be expensive. This is going to be okay because we need to consider, I mean, the issue or the performance with redundancy. But it's expensive, but I get rid of the redundancy. The other thing, another problem here, if we give you like, come up with a decomposition, decompose whatever given relation into a set of sub-relations or the set of relations. And this relation is going to cause, say, we're going to require cause that the data are going to be lose some data, okay? Although we have more tuples, but we're going to lose some information. We can avoid this problem or to enforce that. The only decomposition that you can perform can be used as the lossless one. Or the one that when you allow you in order to reconstruct the relation without losing any information. The third part of the problem here is called dependency preserving decomposition. What does that mean here? Assume that you give you like relation R1. Let's do this one here. Okay. Let me go here. That's okay. Assume that we have a relation R. Okay. A, B, C, D. Okay, I divide this one into R1, it's going to be AB, and R2 is going to be CD. So in order to give me a set of functional dependencies, just for example, A determines B, C determines D, something like this, okay? So the dependency preserving decomposition, that means here, when you check dependencies here, there is no need in order to combine two or more relations together. So in this case, A determines B. The only need to do in order to test this one against the relation R1. Do you need to test this one against the relation R2? No, because these attributes does belong to this relation. CD, this functional dependency required for me in order to test this one against only one relation. Okay. F, there is a way, or there's have the situation to try to change something like F. What if the value of functional dependency given AB determines C, for example, and etc. In order to check whether the AB determines C, for example, assume that the relation R2 is going to be A, B, C, D, or something like this. Okay? In order to test this functional dependencies here, okay, or maybe have, yeah, A, C, D, something like this. In order to test AB determines C, that's required for me to do what? To join R1 and R2 together in order to perform this operation. Because all these attributes that belongs to relation. The AB belongs here, and the C belongs here. Of course, I connect this one using A, required for me in order to perform this kind of, join before to test them. If I have this situation, so in this case, it's going to be like inexpensive. How can you solve that? I can enforce what is called dependency preserving decomposition. Okay? So that means in this case, I'm going to divide my data. I'm going to build something similar to this one, the first case. In the way that for every single dependency, there is no, let's say, dependency required for me to perform join or an expensive operation in order to test whether this dependency is hold or not. Okay? So in order to do the normalization, I'm going to use the lossless decomposition. Okay? There is no redundancy. I'm trying to avoid the unnecessary data duplication. There is redundancy somehow, but we're going to see some of them you cannot avoid. For example, for the instructor, if you have a number of instructors, they belong to the same department. So in this case, it's okay. The department can be repeated in this case. It's acceptable. But don't repeat the department name and the budget and whatever, the location or the building of the department in the instructor list. Oh, that's too much. Okay? But remember, there is redundancy somehow. We cannot eliminate the redundancy 100%. Okay? But we try to, that's why I said avoid unnecessary data duplication and dependency preservation. That's what we try to perform here. Okay? So that means the schema is going to be what? Preserve dependency if the original function dependency do not span multiple tables. If you have a function dependency or set of function dependency, at least one of them span among, let's say, multiple tables, that's means in order to test this one, you need to join these tables. The same case, the second case they give you with R1, R2, with AB and ACD. Okay? I'll remind you with how can you test whether they're lossless joint decomposition or not. This is the way how to test this one. You take R, I give you like R1 and R2, or maybe more R3 and 4. You have to perform, intersection, and see whether it's going to be one of them is going to be form a key either from the R1 and R2. If from key, that means great. Let's lossless decomposition. And we talked about this one before. We said why the key is going to help, because we have a common way or the unique way in order to reconstruct the relation without losing any information, because the key. Okay, dependency preservation. Here we talk about this one here. That means, as I mentioned, we have a set of functional dependencies required in order to test them, required to do expensive operation. What's expensive operation? A joining. Maybe two more relations just to try to test with this functional dependency hold or not, which is not a good idea. So we try to perform that. If we have like this kind of given any functional dependency requiring me to do join to perform this expensive operation with joining in order to test whether this functional dependency or the given functional dependency is a hold or not, that is called not dependency preserving. So I can test this one to see whether it's going to be dependency preserving or not. See if I can test every single functional dependency against only one, let's say, decomposed relation. If any found out any of the set of given functional dependency required for me to perform a join, I cannot test using uniquely only one functional dependency, decomposed relation. Then in this case, we call this one not dependency preserving. We have a instruction here. I can jump this one and give you like the idea how can you do that. Okay, in order to test this, there's one way to perform this one. I will give you an easy way. So the simple thing, there's an algorithm you can test this one. Okay, take a look here. I give you the simple way that I want from you to do if some question that appears to you out in the future. You have what? The set of functions, relation R, set of attributes, and a given set of functional dependencies in this relation R. And we said to check. We decompose this one into the following ways. The first one, R1 has AB and R2 has BC. First, check with one is going to be lossless joint decomposition. Intersect them and check whether it's going to be the result is going to be a key in the relation R1 and R2. R1 intersects with R2, that's means AB intersect with a BC, the common attribute B, and B determines C. Oh yeah, that's key in the relation R2, yeah? So yes, is lossless decomposition, okay? Lossless joint decomposition, okay. I want to check whether it's going to be dependency preserving or not. I'll give you the simple way. Of course, you can apply the algorithm, but this is the simple way to do that. You start with the check A, B determines B. Can I check this one using R1, or I need to combine or join R1 and R2 in order to check this one? A, B, all the attributes are here, so I can test the one using R1, so it's fine. In order to tell whether dependency preserving or not, if not, it's easy to prove. If you found only at least one functional dependency that require from you to join two or more decomposed relations in order to test this functional dependency, then you can stop and say it's not preserving or dependency preserving. B determines C. Required to, can I test this one here? No. Can I test one here? Yes. The only thing you need just to X the relation R2 and I can test. So I can say it's dependency preserved. Or if you want to use this algorithm, you can start with every single functional dependency. For example, A determines B, and try to check whether it can check this one or can be evaluate this one or check whether this given function dependency hold and this given, let's say, decomposed relation or not. So you have to follow this algorithm. I believe this is the easiest way, okay, and the more effective way. Let me give you another example. So the other thing, you take a look here, take a look. Okay, give you this function, relation, the set of functional dependencies given like this. Then after that, it's required from you to do what? Check this one and see, okay, what are you going to have? I give you R1 and R2. I decompose this one as follows. And I ask you to check whether you lose this decomposition and dependency preserving. Check with this one, whether I lose this joint decomposition or not. I take R1, intersect with R2. R1 is going to be AB. Intersect with R2 is going to be AC. The result equal to what here? Maybe A. And based on the table, set function dependency, A determines B. Oh, A determines B is the key here for the relation R1. So it's going to be here, it's going to be R1. So yes. Okay? The second one now, we'll check whether dependency preserving or not. Let me show you something here. The simple thing, I'm looking for something require any function dependency had that required attribute belongs to relations. You cannot apply this one using only single relation. So check this one. AB, this can be used R1. It's fine. BC, B1 attribute here, C here. In order to test this one, I need to join R1 with R2. Oh, that means not depends preserved. So that's all for the first part.